Okay, off we go. As I just noted, it sounds like Canvas is down, and so forget about the attendance quiz. No attendance quiz today, just because of we're offline. So anyway, okay. So picking up where we left off, we were talking about change of variables. And remember the big idea. Why don't I rewind a bit here? We'll go back to here we go. Here's the big idea. Big idea is if you have some integral that's defined on some domain, and that domain is undesirable, right? And I should be highlighting as we go here. You have some integral defined on an undesirable domain. The idea is if you can view that domain as being an image, and specifically as being an image of a domain that you like better, right? That's the trick. Okay, find some way, by hook or by crook, how this happens. It's different in every different circumstance. If your ugly domain is an image of something you like better, then we do this thing called a pullback, right? So that integral, I say I'm going to rewrite everything there in terms of, as I've set it up here, u's and v's, right? Whatever your pullback variables are. And that new integral will, wrong color. There's my little buttons. Okay, hang on. I can't see. These buttons are black on black, and they're really hard to. Oh gosh. Okay, it was rotated. Okay, here we go. Sorry about that. The new integral will be computed on this new pullback domain. Right, so that's the big idea. So it becomes really nice to be able to see a set as being an image of another set. Okay, does that all look familiar? Everybody comfortable with the big picture? So there's the idea of the pullback, and then the other big idea is just the recognition that this little piece of area here and this little piece of area here, of course, can't be assumed to be the same. Check it out. There's this function g that's doing all kinds of who knows what to u's and v's before turning them into x's and y's. And so it would seem reasonable that this amount of area is going to be stretched by some sort of a factor. Now, it might be a less than one factor, right? Who knows? But some factor. And so don't forget to insert that stretching factor to account for that. All right, so those two big things to remember. Okay, so we did an example. We did a couple of examples last time, and now I'm going to show you another scenario where this comes up, and where ultimately change of variables is going to be the tool that allows us to turn a hard problem into an easy problem. Okay, now reminder, what is this stretching factor? And here's our formula for a stretching factor if you're thinking of x and y as functions of u and v. And note in particular, we're taking the partials of the output variables with respect to the input variables. Very importantly, always the partials of the outputs with respect to the inputs. Okay. Right, fine. Okay, now here's the idea. If I have, in fact, an invertible change of variables function, right? I can invert it. I can turn that around and go the other direction. If I go the other direction, I will have, I already forgot what colors I used, but anyway, u and v, now my output variables. And so the stretching factor going this opposite direction would be the partial of the outputs, now u and v, with respect to the inputs, now x and y. Right? So altogether, let's think about this. We've got change of variables functions going both different directions. We know the stretching factor. We know how to write down the formula for the stretching factor of each one of these. And let's consider now what would happen if I had some little region here, whatever that might be, some little small piece of area. And let's ask what happens if that's not the color I wanted. I'm sorry. If I go push it forward over here, well, that's gonna change that area by a factor. In particular, it's going to change that area by a factor of that established stretching factor. And now what if I come back? Well, that's going to take whatever area I had here and stretch it by this recently established stretching factor. So altogether, that orange area is going to be stretched by a factor which is the product of these two factors. And by the way, what do you get when you take something and you push it over and bring it right back? You get exactly the same thing. And that means that the overall stretching factor kind of obviously has to be 1. Yeah.
Why is there an absolute value around
that's a great question. It's it's the formula. If we go back to where we write this down, right? This is part of the formula. It's a very important part of the formula. Why it's part of the formula is ultimately, let's just go back to the substitution rule. Ultimately, the point is that if this stretching factor here is negative, what that means is that forward there turns into backwards here. That backwards there will make this number actually less than, not greater than, this number, and that introduces a minus sign. So roughly speaking, the minus sign here corresponds to a minus sign over here. When we're looking at it with double integrals, we don't think of integrals in that way. We don't think of integrals as being defined on oriented domains. It's just a dumb domain just sitting there. There is no notion of direction.
Because we made up the difference. Sort of.
Yeah, it's just, it doesn't have a notion of direction. So if you look here, right, it's always from here to there. Right, and how you write these down matters, right? But to the tune of a minus sign, and there is no sort of equivalent version of that here. So in some sense, if we were to write single variable integrals more like this, then there would be an absolute value in that formula. Yes.
Does invertibility have any kind of?
Yeah,
is it a factor in this?
It's an assumption. It's something that we always have to have. This is something I mentioned it ultra briefly in the last lecture. If it's not invertible, then it just leads to what I would call obviously awkward problems of duplicating stuff that you've already got. And so once you assume invertibility, then in some sense all that goes away. Is that satisfying? Yeah. Cool. Okay, so so this product is 1. That means that the red and the blue are reciprocals of each other. And by the way, check out how that looks when you write it down, right? That these are reciprocals of each other. It looks like that we're taking the reciprocal of a fraction and that we're switching the numerator and denominator. Said differently, it behaves, again, like a fraction. Now, I cannot emphasize enough. It's not a fraction, right? This thing that looks like a numerator, that's not a thing, right? Certainly not the way I've defined it here. And likewise, this denominator, not a thing, right? So that's not a fraction, but it behaves like a fraction yet again. And that's it's just another motivation for, a kind of a flawed notation is actually kind of helpful, kind of convenient, really. Okay, let me show you how we can use this. Another example. Here's the integral we're interested in. I want to compute that integral. The integral is defined on that's not the color I wanted. Sorry, dark blue. That integral is defined on this region, bounded by those 4 curves, which is this gray shaded region R here. That's a good exercise, by the way, to think through what do these curves look like, and I've got them drawn here, and think about how those curves relate to each other. Helpful exercise. If you get stuck on that, if you're not sure how to deal with that, come talk to me in office hours. I'll be happy to help. But you get a region that looks kind of like this. Pretty weird. By the way, let me address something you may be wondering. You may be wondering to yourself, well, that's extremely weird and unnatural, and when in life am I ever going to experience one of these weird things? Let me tell you where I experienced it. And it was in a thermodynamics class. Right, now a lot of y'all are engineers, and y'all are going to take, I'm pretty sure, at some point a course either entirely on thermodynamics or that will include some discussions of thermodynamics. Right? And in any such course, you're going to have a discussion of what's called the Carnot cycle, the Carnot engine. Does that sound familiar to any of y'all? Maybe? No? Okay, right. Well, you will. And when you do calculations about the Carnot cycle, it turns out the Carnot cycle actually looks a lot like this region right here. And it's literally defined by 4 curves that look a lot like these. Now, the exponent won't be 2. So I cleaned it up a little bit for our convenience just to, make it go down easier in what we're doing. But the point is, structurally, it's a lot like this. So this is a very relevant discussion for at least those of you who are engineers or physicists. So anyway, I think that's interesting. Okay, so what do we do? I mean, what a terrible region. And again, you think about if you were to do this the old-fashioned way, slice and dice rectangularly, you're going to hit those 2 corners. So you're going to get 3 integrals no matter what. So highly undesirable. So what can we do to avoid this? Here's the trick. Wonderful little trick. I did not think this up myself. Somebody showed me. Now I'm showing you, right? So the only reason I know to do this is that somebody did me the favor of showing me. I did not figure this out on my own. Don't think to yourself, I never would have thought of that. Because I didn't either. Here's the idea. 2 of these curves, you will notice, are level sets. In fact, they are level sets of the same function. Right? Everybody see that? The other 2 of these curves are also level sets. And furthermore, they are also level sets of the same function. When this happens, here's the big trick. Take that first function, call it u. Take that second function, call it v, and that is, between the 2 of them, that's going to be what I'm going to call your change of variables function. Now, of course, you're going to notice that function's going the wrong way. What we've done in the past has x and y as functions of u and v, or you might say it as, given how I've set up the variables, the function's gone to the right previously, and now it's going to the left. And that was going to create an element of confusion, and can we even do a pullback? And, pullbacks would take me this way, I want to go that way, we've got a lot of problems. Conveniently, I've got a way of dealing with this, right? If I want my function to go, if I have a function going one way and I want it to go the other way, hey, cool, check it out. Their stretching factors are just reciprocals of each other. Compute whichever one you like. Whichever one's easier to compute is fine. Just compute that, and then take the reciprocal if you need to. Very valuable, very convenient. So now, which one do we need here? Do I need partial uv, partial xy, or do I need partial xy, partial uv? Let me momentarily skip that computation, come down here, and show you how to identify what you actually need. Let's see here. Here's the integral we're interested in. And I know that I want to rewrite it in terms of u's and v's. Again, I look back here, and I've got an integral defined on this domain. I would much rather have an integral defined on this domain. In other words, I want to rewrite everything in terms of u's and v's. Okay, so I would like to rewrite this integral in terms of u's and v's. Said differently, I would like to rewrite dx dy as, well, there's going to be some stretching factor times du dv. Right, now notice I'm not, I'm just kind of thinking through from where I happen to be to where I want to be, and I'm trying to deduce, I'm trying to persuade myself of which one of these stretching factors do I actually need. And so, again, very conveniently, I ask myself, well, what is it that I need to multiply to make that cancellation happen and to make this thing correspond as it's supposed to that thing? And, well, the thing I need to make that work is this one. I need partial xy, partial uv. Does everybody see how I identified that? That's a thought process. It's a strategic choice. I have an integral like this. I want an integral like this. This is the thing, therefore, that I have to stick in there. Okay, so let's compute. Let's compute partial xy, partial uv. And again, unfortunately, I don't have formulas for x and y, so I can't compute the partials of x and y, at least not directly. Now, of course, we could solve. We could solve for x and y here. It's doable. It's fine. That wouldn't be a problem. I don't want to do it that way, right? The point here is not the answer. The point is the method. Let's pretend that we can't solve for x and y. Well, I have formulas for u and v, and it's very straightforward, therefore, to compute partial uv, partial xy. That's just partial derivatives and a determinant, nothing to it. I've identified already that I need partial xy, partial uv. In other words, I need sort of the reciprocal, so just take the reciprocal of what you just computed. What do you think? Everybody see how that worked? Now, there's a different way that you can think about this, also perfectly fine. I don't encourage the following, but one thing you can do is think, all right, well, when the function's going to the right, you're pulling back to the left, and of course you need the stretching factor. The stretch, of course, happens as you go forward, and so you insert it. Anyway, there's a lot of forward, backward, oh gosh, if the variables are the other way, and wait, which way? Do I want to pull that way, or do I want to pull, am I going, you can totally get yourself turned around. Very easy to get turned around. Right? So I encourage not thinking about this in terms of which direction am I going. Let the notation do that for you. Right? As we argued here, the notation will help you to see which factor am I going to need to turn the integral I don't want into the integral I do want. Let the notation help you out like that. Why not? Right? And the notation will always lead you the right direction. Okay. All right, so that's pretty much how it goes. It's a neat trick. And again, you'll notice that we've turned a hard integral into an easy integral. An integral that where we were totally going to hit corners. We were going to have three separate iterated integrals. Now we have an integral on a rectangle, right? Because all of these curves are straight lines, right? I mean, if xy equals 1, and if u is xy, then that's u equals 1. We get that straight line, and thus this rectangle. So really, really clever trick, right? Very, very convenient. The only problem you'll notice is when you got it all plugged in, notice you still have x's and y's in terms of u and v. That you need to rewrite in terms of u and v. I can't do this integral as it is. I need everything written in terms of u and v. Okay, the whole point to this exercise is that I didn't want to have to solve for x and y in terms of u and v. And good news, we still don't have to solve for x and y specifically. And again, if you just take a careful look at what we have here, what is it that I need to rewrite in terms of u and v? I don't need to rewrite x. I don't need to rewrite y. I need to rewrite that whole thing, x to the 7th times y, just only that one thing. Right, so once you have your computation done, forget about your original integrand, forget about your stretching factor, you don't need to convert those. It's only when you combine them and you get your final, eventual, totally pulled back integrand, that is what you need to rewrite in terms of u and v. Okay, so how to do that? I'm sorry to report there's a certain amount of guess and check that's involved in this. It is what it is. Every example's different. Let's see. Here's what I'm going to argue in this case, and every example is different. What we have here is a product of powers of x and y. I need to rewrite that in terms of u and v. Hey, wait a minute. U and v are products of powers of x and y. Right? So ultimately, I need to figure out how to rewrite a product of powers of x and y in terms of products of powers of x and y. And here's my speculation, right? And I hope this seems reasonable. If you have, as I've got here, two products of powers of x and y, if I were to take a product of powers of those products of powers, I feel like we would get another product of powers. Possibly, hopefully, fingers crossed, the product of powers that we're interested in. Is that cool? Everybody see that? This is a speculation. I'm not saying that I know this is going to work. I'm saying I think this is a reasonable speculation. And so this is something you're going to have to do in situations like this. You're going to have to look at, well, what is the form of what I need to convert? What are the forms of the things that I've got? And then what do I think I would, how do these pieces seemingly fit together? So having written this down, it's just a little bit of algebra. And y'all can read that algebra. It's no big deal. You just kind of multiply this out and collect factors. Realize then that means that these exponents have to pair up. Solve for A and B, we win. Is that cool? Everybody with me? Yeah.
Did you just get A and B by as if you had multiplied them without actually multiplying them?
I'm sorry, say again? I just multiplied this out, still not knowing A and B.
Right.
But my point is that here's a product of powers of x and y, there's a product of powers in x and y. If those are going to be the same, then those exponents have to correspond.
If you had multiplied it out, wouldn't it be to the x, x squared a? So then it would be a 2 in front of the a.
What do you mean multiplied it out? You talking about this right here?
Yeah.
I did. That's what this is. Did I do the algebra wrong?
No. I don't think so. But I was just wondering.
Yeah. But so that's what that step is. Does that make sense?
Yeah.
Okay. How are we doing? Anybody else? Everybody happy? All right. Okay, so, and then it's basically all over but the shouting. This then is what you plug in there. Then we have an integral that's entirely in terms of u's and v's, and off you go. Okay. Let's real quick talk about where the stretching factor formula came from. I'm going to leave some of the linear algebra details as an exercise for y'all to think through on your own. As always, talk to me. If you have questions, come to office hours. Happy to help. But the broad strokes, right? We've got this little piece of area in the UV plane. We know that it's, with the colors, we know it's going to get stretched out by some sort of a factor to give us a piece of area in the XY plane. And let's see if we can write down what these areas are. First of all, I have to get my hands on what we're talking about. This vector is in the E1 direction and has magnitude du, because that's the width du of this little rectangle, subrectangle. So that's E1 du. And the derivative matrix is what turns that into its image. Its image is going to be that edge, so its image is going to be derivative matrix times E1 du. Right, so let's just flash back to chapter 2. Chapter 2 turns input vectors into output vectors. So you do that for both sides. Then we can argue that this area, that's just the area of a parallelogram in the plane. We know that's done with determinants. And now you've got a little bit of a linear algebra problem. This is a good exercise. Again, come talk to me if you get stuck, but you can rewrite that like so. And now check it out. Our output area, we can see, is the input area times a factor. And so that factor, right, the thing you multiply by green to get blue, there it is. Pops right out of this calculation. And as we claimed, it's the absolute value of the Jacobian determinant. Is that cool? Broad strokes, does everybody see kind of the strategy there? Okay. All right. I think it's a healthy exercise. Think through that linear algebra. Make sure you still remember how that stuff works. It'd be good for you. Come talk to me if you have any questions. Off we go. 3 dimensions. Here's the good news. It's strategically identical. It's the same move. We're going to take some domain that we don't like. And by the way, I really, really don't like this domain. That domain is a horror story. Look at all those corners. As you're slicing this up, you're going to be hitting corners all over the place. You're going to be side-swiping edges all over the place. You'll be side-swiping faces several times. Each one of those many slices you're going to have to look at. It's not a rectangle. When you slice them up, you're going to be hitting corners and side-swiping edges, and oh my God, right? This would be a nightmare. It's unthinkable. Completely intractable. And the same strategy, if you can find, by hook or by crook, how you can view that as an image of something nicer. Again, here's the dream, right? The dream is a rectangular box. It's got everyone's favorite domain for a triple integral. Then we're going to make the same argument. We're going to say, well, look, first of all, we can plug in. That's pull back, right? So the integral here turns into an integral there. Awesome. That's exactly what we wanted. And then again, don't forget to insert your stretching factor. After all, G is going to stretch things out. And I'm just going to assert that the stretching factor, again, is the absolute value of the Jacobian determinant. We have an analogous notation. It's exactly what you would hope, exactly what you would think. Okay. All right, so let's see an example of this in action. Real quick, I have to put down one quick little theorem. This is a very easy self-check y'all can do. I claim if you have a linear transformation, linear transformations, Jacobian matrices are the same matrix as the matrix that defines the linear transformation in the first place. How about that? Isn't that convenient? Super handy. Nice fact to remember. I want to make sure to remember that one. It'll save you a calculation and then a resulting confusion. Right? Because there's a little bit of an eyebrow raiser. You think, but surely not. Surely this is going to be something different. But it is. So the way you're going to prove this, and again, this is an easy little exercise. Just write yourself down a little 2x2 matrix, for example, or 3x3 if you feel like it, whatever. And then write down the corresponding linear transformation by multiplying a times x. Take the corresponding partials, ascend them accordingly, and you will find that your derivative matrix is, in fact, sure enough, exactly that original matrix. Straightforward calculation. Okay. All right. So now with that established, let's look at this example. This is another nightmare problem that we're going to turn into an easy calculation. Our domain is a parallelepiped defined by 3 edge vectors like so. And now again, just for the horror of it all, right? Let's think through if I were to slice this up, and you might be thinking, oh, well, that's not that bad because the faces are all flat, and that's kind of nice. You're not going to sideswipe any faces. That's cool. But there's still 8 edges. 8 vertices. One's going to be where you're going to start. One's going to be where you end. There's going to be 6 vertices in the middle. That means you're doing 7 integrals. Already highly undesirable, right? And here's the thing, it's worse than that. Because again, each one of these slices, think about what happens. You know, what kind of a shape do you get when you slice a parallelepiped? And answer, you get different shapes depending on where you slice the parallelepiped. Sometimes you get a triangle. Sometimes you get a parallelogram. Sometimes you get a hexagon. That's hard to visualize, which is yet another reason we don't want to have to go down that road and think in terms of what do these slices look like. But then let me just point out, if one of your 7 slices is a hexagon, you're going to have to slice up that hexagon. And again, you're hitting corners all over the place. It's a nightmare. There's going to be on the order of about 20 different iterated integrals to compute. Absolute non-starter. We definitely don't want to do that. Yeah? Okay, so here's the trick. Cool trick. Wish I'd thought of it. Again, somebody showed me this when I was about y'all's age. Great trick. When your domain is a parallelepiped, take those given edge vectors, make those the columns of a matrix. Let that matrix, let that matrix define your linear transformation, and let that linear transformation be your change of variables function. That's the move. That's the magic trick. That's what makes it all work right there. So make sure to memorize this. Whatever the edge vectors, those the columns, that's your linear transformation. Okay? And I claim it's all downhill from here. So let's see here. I am going to assert that my pullback domain is just going to be the unit cube. Again, everybody's favorite domain for a triple integral. Unit cube, 0 to 1, 0 to 1, 0 to 1. Can't beat that. Right? So, okay, how do I know? I mean, I'm asserting that the image of this is this. How do I know that's true? Well, let's look at the edges one at a time. What's the image of E1? Well, the image of E1 is going to be the first column of my matrix, right? Columns are the images of the standard basis vectors. That first column is that first vector, namely it's the first edge of this parallelepiped. And likewise, correspondingly for the other edges. And then by linearity, we win. So, totally awesome idea. Works perfectly. And all we again have to do at this point is wave the magic wand and say pull back. Right? So the integral that we had here, defined on this nightmare of a domain, we pull back, and it turns into this integral. We'll worry about our stretching factor in a second, but that integral, which is defined on totally awesome domain, massive win already, right? I'll pretty much tolerate any integrand if I can have the unit cube as my domain because it's so nice, right? Yes?
Can we assume that for like most shapes in 3D that it's a stretching factor of, or like the uncomfortable shape is a linear transformation of
I wish, but sadly no. Yeah. And so there is this constant problem of how do I view, I need to figure out what is my change of variables function. And it can be tricky. And I'm going to show you, I have a couple of strong favorite change of variables functions when you're in 3 dimensions. And I'm going to show you those later today. Yeah.
But do we always assume them for like cubes and like rectangular coordinates, or just?
I don't like the word assume. It makes mathematicians get the jitters because I don't know. I mean, you're asking me to make a confident statement about scenarios that you haven't even described to me. I don't know, right? So I mean, always I'm not gonna, right? Probably not. It's a good thing to try, right? Especially when you have something that's got a lot of flatness about it. I mean, it's reasonable to think in those terms, but I wouldn't say always. Yeah. You had a question. Yeah.
I guess kind of similar, like in what cases should we assume that we can't use this unit square multiplied by matrix A trick?
This trick is tailor-made for parallelepipeds that have one vertex at the origin. So and in fact, if you turn it around, I'm sorry? Yeah. If you turn it around, I mean, if you say, hey, when can I use the unit cube with a linear transformation? In fact, anytime you use a unit cube and stick it into a linear transformation, you'll always get a parallelepiped with one vertex at the origin. So yeah, this is a narrow example. Okay, so let's see how the rest of this calculation plays out. We compute the stretching factor. We saw previously the stretching factor. The Jacobian matrix is the same as the linear transformations matrix, so that's why I don't have to compute the Jacobian. I already know that this is that Jacobian. And so you just take the determinant of that matrix, that's your stretching factor, and we win off to the races. Is that cool? Everybody happy? Okay. All right. Okay. All right. Actually, let me not get ahead of myself here. Flashbacks to chapter 1. Remember we talked about polar coordinates, right? We talked about cylindrical coordinates, spherical coordinates. And you can think of those in different ways, and I have this personal preference. I like to think of them as functions. And this is where one of the big payoffs to that is going to be. Because if you think about polar coordinates, for example, as a function, right? R and theta go in, X and Y come out. Check it out. It is a change of variables function. Right? This is a function from 2 dimensions to 2 dimensions, and if I have a domain over here, I can talk about, now why I'd want to, we'll consider that in a moment, but I can take some domain here, I could pull it back through the polar coordinates conversion function, and I would have a new domain back here in the r theta plane. And it turns out this is one of the very best change of variables functions you will ever find. It is useful extremely commonly. Right? So, likewise, by the way, let's try to get this all on the screen at once. Likewise, not only is polar coordinates, but also cylindrical coordinates and also spherical coordinates. We haven't thought of them in this way previously, but they are functions, and you can therefore choose to use them as change of variables functions. In each case, you can compute the stretching factors. Everybody should do these once in their lives. Give it a try. It's not that big a deal. Right? The hardest one by far isn't that hard. It's the spherical one, because you have, weirder functions to deal with. When you write down all the partials and assemble that matrix and look at the determinant and you're thinking, oh my gosh, this is going to be a trig explosion, right? And the trig is going to take up an entire page. Oh my gosh. What happens is the Pythagorean identity kicks in like 3 times, if I remember correctly. And so it simplifies massively. And notice how simple that stretching factor is. It's just rho squared sine phi. That's all it is. Nice and simple. Okay. All right. Now let me zoom in real quick. So our stretching factor, don't forget, our stretching factor has these absolute values in it. This is not a minor note. It is something you have to take seriously. You will get wrong answers and your bridge will fall down if you don't remember those absolute values, right? So, my Jacobian determinant is R, my stretching factor is the absolute value of R. Oh my gosh, am I going to have to deal with absolute values every time I do this? Here's the move. Very reasonable choice. While we're doing change of variables, I think it would be a good choice to restrict our attention only to non-negative values of R. Right? Just disallow the idea that you would use a negative r. Personal choice. You're not legally bound to do this, right? But you are strategically encouraged. You strategically benefit from promising you will only choose non-negative r's, because then the absolute values go away. And now you don't have to deal with absolute values anymore. Is everybody cool? Everybody on board? Okay, so great choice. Likewise, with cylindrical coordinates, just choose r to be non-negative. Just, again, personal choice. And you get this massive benefit. Very similar for spherical coordinates, importantly different. Let me point out, a lot of students are under misimpressions from high school. A lot of people have been told, well, rho is pretty much the same as r, and anyway, if you're doing spherical coordinates, if you see a rho, think r, it's pretty much the same thing. Not at all. Pretty clearly not in this case anyway. Here we go. We've got this Jacobian determinant whose absolute value I have to deal with, and I want this stretching factor to simplify nicely. If I just merely promise to only choose positive values of rho, does that ensure that the minus sign will fall away? Nonsense. The sine theta is the problem, sine phi is the problem. It's got nothing to do with rho. Rho can be as negative as it wants. I don't care. It's going to get squared anyway. Whatever. Right? Does everybody see that? Okay. So again, don't fall for this idea that spherical coordinates is basically polar coordinates. It's importantly, and I think pretty dramatically different in this case anyway. So what do we do? And what we do is we look at this expression and we realize if I just choose instead, color choices. If I choose to make phi between 0 and pi, that means sine phi won't be negative, and that means that I can throw away the absolute values, and again, life is good. Is that cool? Yeah.
How do you choose?
I just stand there with my hand on my favorite book and say, I promise I will not choose any values of phi other than between 0 and pi. It's literally just personal choice.
But when do you get to pick what value?
Yeah, well, just so as you're doing your calculations, as you're doing your pullback, right? Just make sure to look at what the pullback that you've decided on, and just make sure that phi is in fact always between 0 and pi. And if it is, you win. Is that cool? Yeah. Okay. All right. Okay, so let's see an example of this in action. So let's look at this integral. Oh gosh, with the colors. Let's look at this integral here. Right, that integral is defined on the first quadrant portion of the unit disk, which looks approximately like this. Now, you may be thinking to yourselves, hey, you know what, that domain's not that bad. That's just a quarter disk, whatever. But here's the problem. Whichever way you slice, you're going to have to deal with this curved top, sort of edge, if you will, right? And that is a circle, and there's, when you solve for x in terms of y or y in terms of x, whichever way you go, you're going to have a square root, and that means there's square roots in the calculation, and this calculation is doable, but it's annoying. Right? It is suboptimal for sure, and by the way, with a worse integrand, it could very well turn into something that's intractable. Right? So, suboptimal. Let's call that plan B. So the clever move is to notice that this domain that we don't like is the image of this rectangle. And you can just kind of think it through one edge at a time. Here, let me clear off for colors. Let's think about, for example, what is this edge right there in this rectangle that I've drawn back here in the r theta plane. That edge is where r is equal to 1. And notice, as I've set this up, r is equal to 1, and then theta starts at 0 and increases up to pi over 2, all while r stays 1. That edge becomes exactly that edge. Everybody see that? Likewise, this is that, and this is that. And here's the weird one. This edge, this whole edge on the left, that whole left edge in red is where r equals 0. And so the fact that theta is doing something, whatever, who cares? That whole edge sort of pinches down to that single point. Everybody on board? So, sweet. My undesirable domain I have now successfully viewed as being an image, by the way, image through a familiar change of variables function, right? This polar coordinates conversion formula. The image of this much more desirable rectangle, and do the pullback. Don't forget your stretching factor. Life is good. No more square roots. Is everybody happy? Everybody see what happened there? Okay, so cannot emphasize enough. Don't forget that stretching factor right there. You do have to do the pullback, obviously, and in doing the pullback, you got to think about, okay, what is x squared plus y squared? How do I write that in polar coordinates? Well, of course, that's r squared. Again, don't forget your stretching factor. And then easy integral, rectangular domain, constant bounds, power rule, no fractions. Well, okay, the fourth. Right? But no scary fractions, right? And easy calculation. Much more desirable than doing this the old-fashioned way. Okay. All right. Now, I want to give you a different take on what's happening here, a different way to think about what we're doing here. And it's based on the following observation, and that is that if you have some domain over here, and you pull it back, and you have some new domain over here, hopefully nicer. Notice, as I do theta slices, each one of these theta slices represents a constant value of theta. Each slice represents a single constant value of theta. Well, I know what those look like over in the xy plane. A single constant value of theta. Each one of those looks something like this. Right, so the big idea is when you're using the polar coordinates conversion formulas as a change of variables function, mouthful, that's a lot to say, right? But when you're doing this, you could draw your pullback and look at the slices over here, or you could say, whatever, anything I need to see over there, I can see it over here. I can literally see those theta slices. They're just now sort of radial. They're not parallel lines perpendicular to the theta axis. Now they're just rays, if you will, coming out of the origin. Right, so with this point of view, let's do that problem that we just did. Let's do the whole thing over again. Now streamlined. Yes, we have this domain. Yes, there is the pullback domain. Yes, I should be slicing up that pullback domain. But look, that slice, this very first slice that I do down here where theta equals 0, cool. I can see that right there. I don't need to look at the picture on the left. As I continue to slice, okay, fine, yeah, all good, but I can see what those slices look like right over here. I don't need that picture on the left. When I get to the end, right, I end at that slice where theta is pi over 2. Yeah, right, cool, and I can see that over here too. Right? These radial theta slices, I can just see right here in the picture. They start when theta is 0, and they kind of go around until I get to this last piece where theta is pi over 2. You don't need the pullback picture at all. This is artistically very helpful. You don't have to draw a new picture. Does that make sense? Really nice. So this is what we call doing the integral in polar coordinates. There is a change of variables underlying it. We are doing a change of variables. There is a pullback domain. We are slicing up the pullback domain on it. For sure, right? We don't have to think of it that way. We can just think of it by this kind of slicing in the XY plane on our original domain. No new picture needed at all. Okay. All right, so that's in practice, how people think about these kinds of problems. Here's another example. Let's let our domain be the unit disk. So here it is. Unit disk here. And let's start slicing it up. And I'm going to start where theta is 0. And then, by the way, as theta increases, I keep slicing like this and continued slices, yada, yada, yada. The slices keep going until I finish and get back to where I came from, by which time, of course, theta would have gone all the way up to 2 pi. So my bound's 0 to 2 pi. I don't have to draw any pullback domain, just 0 to 2 pi. Oh, I see I'm out of time. Okay, we'll pick up with this example. We'll pick up with that example next time. Okay, see y'all later. Have a good rest of your Monday.